Welcome to this video on an introduction to rotational dynamics. If you haven't watched the previous video, this is the content that we covered, which is an introduction to rotational kinematics. And this is where we just looked at all the different equations from a translational standpoint and then switched it to the rotational analog of the same thing. And it's important because I'm going to reference some of these terms and symbols, so I would check those out. Alright, so here I have a scenario. I have a wheel, and this wheel is going to roll from position A to position B. So in this case, again on the right, we're going to be looking at the translational motion of the ball. Now what I want to do is draw a force diagram for this ball and use that to help write a net force statement. So I'm going to say that there's some weight acting on the ball by the earth. Then I'm going to say there's a normal force pushing up on the ball by the ground or the earth. And then let's say that I'm physically going to be pushing this the whole time. So I'm going to add here a force applied, on the ball by some, person pushing it. And let's say that there's a little bit of friction as well. So I'll add just a little bit of friction here, and I'll say that that's coming from the ground ball interaction. Now if I was going to write a net force statement here, what I'm going to say is that the force applied is greater than the frictional force, and therefore when I write my net force statement in the horizontal, which I refer to as x, I'm going to say that that would be notated as force applied minus friction equals m times a. And then once I found a, I can find all sorts of other things, right? Using the other kinematics equations that I have, I could find the displacement, or its final position after some, given amount of initial speed and acceleration and a given amount of time. I could also find its velocity after a given amount of time. So there's a variety of things I can do once I've shown what the acceleration is and how I got the acceleration. Now, technically, what we've been looking at so far in physics up to this point is really just what we call sliding motion. So the sliding motion means that I haven't taken into account the fact that the ball is rotating as it moves up to point B. Basically, all I'm saying is that the friction here is just going to be constantly pushing backwards as I get to point B the whole way through. However, we know that it's preferable oftentimes to have the wheel roll rather than slide. And if you've ever been on ice, you know that that's kind of scary, right? So we want to now add to our model and see what we can get. So we're talking about a net force here, Newton's second law, showing that unbalanced components make for an acceleration rather than a constant velocity. Now let's look at what's causing this to rotate. It's not really directly the gravity or the normal force or necessarily the applied force, because even if I had applied force, if there was no friction, the ball wouldn't rotate. So I'm going to think about this. The ball is going to rotate clockwise. So this is going to become an important description in the direction it rotates, and I'm going to call this, it's going to go in a clockwise direction. So if I marked a little spot on the edge of the wheel, as I started to push the car or the wheel, I would see that spot translate down or rotate to this, as I go along here. Now I know that if I get rid of friction, the thing will stop, this wheel will stop rotating. So what I'm going to say here is that the force that is causing, and notice I'm taking time to write this out because it's so important in understanding rotational dynamics. The force that is causing the rotation is the friction between the ball and the ground, or the wheel and the ground. So just change that up. This should be for the wheel and the ground. One way to figure out which force is causing the rotation is to eliminate each force and say, would it still rotate? And think about your common sense examples from your everyday life. In this example, I know that if I make less friction on the ground, my car slides rather than rolls. So what I'm going to do here is I'm going to say now that I've identified this fact that a force is needed to cause something to rotate. That's the key terms that we really want to identify. A force is needed to cause a rotation. And what we refer to this as is torque. So torque is referred to as, in some ways, the ability of a force to cause an object to rotate. Okay, and that's referred to as a torque. It's the ability of a force to cause an object rotation. Now, technically, there's an additional part to this to the definition, and it's the ability of a force to cause a rotation around some axis of rotation. So over here, the axle or the center of the wheel will be what we call the axis of rotation. So the axis of rotation is an important point that we have to highlight. Now, if you think about it, if I pushed on the ball straight along the axis of rotation, or I keep calling it a ball, but the wheel, if I pushed on the wheel directly at the axis of rotation, okay, so along this like that, it would just slide, it wouldn't turn, right? If I pushed up like this at that instant, and this axis of rotation was fixed, it would start to spin. So if you think about it, the friction right here between the ground and this wheel has to be pointing this way, right, to cause, so I'm going to label this here as the force of friction between the wheel and the ground, and that's the force that's causing the torque. The more friction I have, the more torque I will have. So what I'm going to say here is that torque, which we symbolize with the Greek letter tau, torque is directly proportional to force. So the more force I push with, the more torque I get. Now, this distance from the axis of rotation to where the force is applied is referred to as, sometimes as a lever arm. I'm just going to refer to it right now as this R position. It's the distance, so we can write here the distance between the axis of rotation, so axis of rotation, to where the force is applied. So that's an important, very important term. And it turns out that the further away I push from, the more torque is applied. And you can think of this with a door. If you're trying to open a door, if you push closer to the hinges, which is the axis of rotation, you have to push a lot harder to rotate the door. That's why the door handle is located on the farthest edge from the axis of rotation. So far we see here that we have that torque is going to be equal to force times R. And I'm going to actually make this a cross product, and we'll talk about what that is in the next video as we get a little bit more detail here. But the main thing to look at here is that I have net force, and the rotational analog of that is net torque. So I'm going to write here that net force in the most general sense equals mass times acceleration. Here I'm going to say that net torque, one of the things we show that it's equal to is force cross R, but that doesn't look very similar to this. So what I'm going to show here is that torque, if you have more torque, if you push harder here, you're going to cause the position to change faster, so that's going to have something to do with angular acceleration. And then instead of talking about just mass, we're going to talk about what's known as the moment of inertia. And this is the point at which many students go, oh my gosh, this is so confusing. Moment of inertia. Now I'm going to show you in the next video why the moment of inertia and this cross product are really not that confusing at all. They actually have a lot of common sense embedded in them, and we'll learn exactly how to do that. So we're going to say that torque can equal these two things, and you can see how the analog between these two situations, I alpha and MA, look very, very similar. So we'll pick up there in the next video.